Okay, 10.13 notes, radius and interval of convergence of power series. So the first part of this note is just a reminder what a power series looks like. Notice we have two types of power series here. The first one is just when C is equal to 0. That's why you don't see the minus C anywhere. Important part here is remember the domain of a power series is the set of all x values for which the power series converges. So the domain is all x values where it converges. Okay, then it says note, the center is always part of the domain. And you're going to understand why once we're looking at some of these examples. So there are three ways a power series may converge. The first way is that it can converge to an interval. For example, let's say we have an interval from A to B where the center we label as C. Okay, that means it can have convergence anywhere on this interval. It could include the bounds A and B. It could not include the bounds A or B, but it will always include C, the center. Okay, makes sense because the center is in the middle of the interval. Okay, these sections here. So this first section, so from the beginning bound to the center and from the center to the last bound, these are called radius, okay, which we denote as R. So R is equal to the radius slash distance from the center to the edge of the interval. So no matter if that's the start or the end of the interval. The second way is that it can converge to all real numbers, okay, where x belongs to the real numbers. Okay, lastly, it can converge to the center, and remember that's x equals c only. Okay, so it can converge to an interval, so an entire part of that interval. It can converge to every single real number, so it's not restricted by an interval, or it can converge only at the center value. So in order to find the interval of convergence, we need to use the ratio test. Okay. For the ratio test for interval of convergence, we have some different guidelines here. So the ratio test is still this part. It's still saying that we need to take the series, do the absolute value of the series, and make sure we do a ratio of a sub n plus 1 over a sub n. Well, if that limit is less than 0, this tells us that the series is going to converge to an interval. Okay. If the limit is equal to 0, this tells us that the series is going to converge to all real values, all real numbers. And if the limit is equal to infinity, then the series is going to converge only to the center. And remember, the center is x equals c. So we need to remember the ratio test, but we don't need to recall when it converges or when it diverges, since we only care about when it converges. Okay, and then there is specific qualifications for it to see if it converges to an interval, the center, or all real numbers. And so we're going to use the ratio test to find the radius and the interval of convergence. So let's start with number 1. Number 1, we have the summation of n equals 1 over to infinity of n over 3 to the power of n times x minus 5 to the n power. So remember, with the ratio test, we need to do n plus 1 and divide it by a sub n. Okay, so since we already went over the ratio test, I'm not going to go step by step by step on how to simplify it. Okay, but I am going to still set up that part of the ratio test. So we have the limit as n approaches infinity of the absolute value of n plus 1 over 3 to the power of n plus 1 times x minus 5 to the power of n plus 1 times the reciprocal of a sub n, which means this is 3n over n times x minus 5 to the n power. Okay, remember with exponentials, we can rewrite these terms to be 3n times 3, and this one x minus 5 times x minus 5 to the power of n. And so what's going to happen is some things are going to cancel. And so we're left with the limit as n approaches infinity of n plus 1 over n times 1/3 times x minus 5. Okay, so if I take the limit as n approaches infinity, that means I'm really only looking at this part here. Okay, and since they have the same degree, that means as they approach infinity, this is going to approach 1, which means that in this entire limit has to be less than 1. Okay, so I'm going to use those rules to say that it's less than 1. Okay, so if it is less than 1, if we go back up to our definitions, that tells us it's going to converge to an interval. So we need to find that interval. Well, in order to find that, we're going to look at everything else. We're going to look at this part. And we are going to do the absolute value where this is less than 1. And so we have the absolute value of 1/3 times x minus 5 less than 1, which means negative 1 is less than 1/3 times x minus 5 less than 1. Doing our algebra, we get 2 is less than x less than 8. Okay, from this part, we cannot just stop and say this is our answer, because remember, even though it converges on the interval, we need to see if it also includes the endpoints or if it does not include the endpoints. So our next step here is going to check the endpoints. Okay, and if they converge, then they're included, but if they diverge, they're not included. Okay, so let's go ahead and check x equals 2 first. And so we're plugging in x equals 2 into our original series at the top. And so this gives me the summation of n equals 1 to infinity, n over 3 to the power of n times 2 minus 5 to the power of n, which reduces to n over 3 to the power of n times negative 3 to the power of n, which reduces to negative 1 power of n times n, which diverges. Okay, that means x equals 2 is not included in the interval. So now I do x equals 8. So the summation of n equals 1 to infinity of n over 3n times 8 minus 5 to the power of n. This gives me n over 3n times 3 to the power of n, which diverges, which means x equals 8 is not included in the interval. And so for my answer, I have 2 is less than x less than 8. And then the next part is I need to find my radius. Well, my radius is always going to be the absolute value of my upper bound minus my lower bound divided by 2. Okay, so 8 minus 2 is 6. 6 divided by 2 is 3. So this entire part is my answer. Okay, let's look at the next example. Okay, number 2. I'm going to do the limit as n approaches infinity of 3x minus 2 to the power of n plus 1 times 1 over 3 times x minus 2 to the power of n. What's going to happen here is as n approaches infinity, I know that this whole thing is going to be less than 1. Because remember, I'm checking, is it less than 1? Is it 0 or is it infinity? Okay, so this is going to be less than 1. And so if I simplify this, which means I cancel things out, I get the absolute value of x minus 2 less than 1. I then solve that out, so negative 1 less than x minus 2 less than 1 means I have the interval 1 less than x less than 3. So then I need to check my endpoints. So at x equals 1, I have the summation of n equals 0 to infinity of 3 times negative 1 to the n power. This diverges, so x equals 1 is not included. And then I do x equals 3. So the summation of n equals 0 to infinity of 3 times 1 to the power of n also diverges. So x equals 3 is not part of the interval. And so for here, I have my answer of 1 less than x less than 3. That is my interval of convergence. And then to find my radius, I do the absolute value of 3 minus 1 over 2, which is 1. So this would be my answer. Okay. Again, when I'm checking my endpoints and I'm determining if this diverges or converges, I'm looking back at the rules that I've learned in previous notes, so at the beginning of Unit 10. So I'm not showing you every step here to prove convergence or divergence because we've already learned about it. Okay, so just know I'm not just pulling this out of thin air. I'm using my knowledge from the beginning of Unit 10. That's why it's very, very important that you memorize that flow chart that is at the end of 10.9. So your first packet of Unit 10 notes. Okay, let's look at the next example. Okay, so I have the limit as n approaches infinity of the absolute value of x plus 2 to the power of n plus 2. Remember, we're always adding 1 to n. Over n plus 1 cubed times n cubed over x plus 2 to the power of n plus 1. Simplifying this gives me the absolute value of x plus 2 over 1 times n cubed over n plus 1 cubed. Okay, again, as n approaches infinity, I have n cubed over n cubed. They have the same degree, so I look at the coefficients, so this is definitely going to be less than 1. Okay, so then I'm checking the other part of it, not the ends. This went to 1. Okay, so now I'm looking at this part. And so I have negative 1 is less than x plus 2 less than 1, which means I have negative 3 less than x less than negative 1 as my interval of convergence. I need to check the endpoints to make sure that, to see if they are included or not included. And so first I'm going to say x is equal to negative 3. So I have the summation of n equals 1 to infinity of negative 1 to n plus 1 over n cubed. This is going to converge, which means x equals negative 3 is included. Then I'm going to do x equals negative 1. So it's the summation of n equals 1 to infinity of 1 to the power of n plus 1 over n cubed, which reduces to 1 over n cubed. Okay. This is a p series where p is greater than 1, so this is going to converge. So since both of them converge, that means both my endpoints on my intervals are going to be included. So my answer is going to be negative 3 is less than or equal to x, less than or equal to negative 1. And then I just need to find my radius, which is still the absolute value of the upper bound minus the lower bound over 2, which gives me 1. Okay, this is my answer. Okay, next example. So I have the limit as n approaches infinity of the absolute value of 2n plus 2 factorial times x to the power of 2n plus 2 over n plus 1 factorial times n factorial over 2n factorial x to the power of 2n. Simplifying this, I get the absolute value of 2n plus 2 times 2n plus 1 times 2n factorial. 2n factorial times n factorial. Okay. All over n plus 1 times n factorial times 2n factorial. Okay, so I already did some reducing here. That's why you don't see the x to the power of 2n plus 2 in this part right here. Because technically what I did is I'm also separating my n's and my x's. And so this is times x squared over 1. Let's cancel some things out. So I have n factorial and 2n factorial. And so here I end up having an n squared over n. So that means my numerator is going to get larger faster than my denominator, which means this entire limit is going to equal infinity. And so remember, if we go back up to the rules, if it equals infinities, that means it only converges at the center. Okay? And if it only converges at the center, that means we don't need to write an interval at all. So I'm going to say converges at the center. And in order to find the center, if we're not setting up our interval here, is remember in our initial definition, the center is C. So if we look up here where this x is, remember this is technically x minus c. Well, since there's no c value here, it's really x minus 0, and that's how they were able to just write x. So that means c is equal to 0, so our center is x equals 0. Okay, and if our center is x equals 0, that means our radius, which is also going to be the distance to our center, is not going to have a distance because the center is 0, so the radius is also 0. So these are my answers. Okay. Last example. So we have the limit as n approaches infinity of the absolute value of x to the power of 3 times n plus 1 over n plus 1 factorial times n factorial over x to the power of 3n. This is going to simplify to the absolute value of x cubed over 1 times 1 over n plus 1. So as n approaches infinity, notice we have 1 over n, so this is going to approach 0, which means this entire limit is going to equal 0. And if we look back at our definition, if the limit of this series approaches 0, then this is going to converge for x belonging to all real numbers. So you can either write x belonging to all real numbers, the fancy R, or you can write it in words, all real numbers, or you can write it to negative infinity to positive infinity. Okay? And in these cases where it is going to equal 0 and it converges on all the real numbers, that means the radius you can just write as infinity.